for it. All right, so it is recording. So I'm following along the notes that I posted. You guys can hear me okay? I'm hoping. Okay. And you can see the whiteboard. If it gets dark, let me know. If I wear my glasses, I get a reflection, and so I can't see very well without my glasses. Yeah, it will work. So we're going to talk about we're going to talk about liquids. And what makes liquids special, different from solids, is solids have a regular pattern, whereas liquids are always flowing. But the thing that keeps them, they're still close together, the molecules in them, is they have what's called IMFs. Do you like my gnomes? They're here in place of you guys. You can identify with one of the gnomes. So IMFs is what today's lecture is about. And so IMF stands for intermolecular forces. So the I and the M and the F. So these are attractive forces. And that is the key word, is attraction. It is always electrostatic. And so the term electrostatic just means positive, negative, attracts. So the positive, it's ionic. The very first one we're going to talk about is ionic. So ionic bonds are not truly a bond. They're actually just an attraction between positive and negative. The only true bond that exists is a covalent bond. And so a covalent bond, things are actually attached. So the analogy that I give is your shoulder is attached to, your arm is attached to your body by your shoulder. And you can't pull your arm off just by pulling. So if I had Edward just tug and tug and tug, he couldn't pull my arm off. These are attractions. So if you're holding hands with somebody, you actually can let go of the hand and the person goes away. And so that's what IMFs are. And this might show up some places. I've tried to go through and I don't always catch it. I don't think the term is the correct term, but everybody uses it. I sometimes say it is always abbreviated IMF. Some places you might run into it where I call it an IPF, and the P, it just means interparticular forces. And this is back to the question that Aaron asked me today. Ions are not technically molecules, and they're not atoms. And so the term particle, so particular means a particle. And so this means it could be an ion, it could be an atom, it could be a molecule. And so it was my attempt for 10 years to like somehow get out there and get this terminology changed, but my attempt did not work in the big world. So we're gonna go with IMFs, but if you run into IPFs, it's just me trying to, so a molecule and an ion are not actually the same thing. All right, I have to find my eraser. Well, I'll have to use the squid hat. See, the squid hat comes in common in use. And since we're gonna get to water, so the four types are ionic, H bond, dipole, and then the fourth one has 4 different names. Right now, I'm gonna call it London. And so, can you guys see the screen or is there glare? We're okay? Okay, so ionic H bond dipole in London. So this goes from the strongest to the weakest. And I want to walk through each type of these. And again, it's always an attraction between a positive and negative. So ionic, you already know. We've talked about that a lot in 221. It would be something like sodium chloride. So the sodium has a positive area, has a true positive, and the chloride has a negative. In terms of if you see a chemical formula, you're just looking for metal, sorry, my handwriting with these, a metal and a non-metal. I think I talked about that the very first class. And we talked about those a lot in 221. So wherever you took 221. This is the strongest type of intermolecular force, and we call it an ionic bond, but again, it is not truly a bond. It's just a really strong attraction. All right, I'm going to skip H bonds, and I'm going to come back to them. Dipoles are anytime you have polar attracted to a polar. So these dots are the attraction. And the best example, the easiest example to show here would be HCl. So this here, this line here is a covalent bond. So that's why we did all this stuff with Lewis structures and organic. So the line is a covalent bond. Those are, the hydrogen and chloride are attracted to each other. So the I means intermolecular, and so that means there has to be two molecules at least present. And so it's an attraction between two different molecules. So my lines are the covalent bond, and then the dots are the attraction. And the attraction is between a positive and negative. So if you remember, I think it was the very first homework set, the very first lecture, I started drawing these funky little, they look like partial infinity signs. They stand for a dipole. So the chloride has a negative dipole, it's pulling, and the hydrogen has a positive dipole. So there's an attraction between this area of positivity on the hydrogen to the area of positivity on the chloride. Up here with ionic, again, it is just an attraction between the sodium and the chloride, but it's a bigger attraction because you have a full charge displacement, whereas this is just partial charges. So what an H bond is an extreme dipole. So an extreme dipole, it is a dipole, but it just is the biggest dipoles there are. They're much bigger. And this is back to your periodic table, and I forgot to mention that. So hopefully you have your periodic table, but it's why we talked about the electronegativity in the very first lecture also. This is NOF, so NO and F. Those are the three most electronegative. They're the greediest. And so if you put a little G in front, it's the gnome's hat. So these hats are called NOFs, which is perfect. They're the original chemist. Anytime you have a hydrogen attached to either a nitrogen, an oxygen, or a fluorine, you have an H bond. And that's why it's so special, because water. So again, these are covalent bonds. The lines are covalent bonds, but if we draw another water molecule, and water does have that bend, you will get an H bond between the hydrogen of one water molecule to the oxygen of the next one. So whenever you have a hydrogen attached to NO or F, you will get this attraction to another NO or F. And that's because the oxygen is negative and the hydrogen is positive, and that huge polarity in this covalent bond makes it an extreme dipole. All right, one other thing I left out is, I'm sure it shows it this way. So in your notes, it calls this third one a dipole-dipole. And so technically, it is always an attraction between two polar molecules. So you have to have two things present. So it is correctly called dipole-dipole, but it gets really tiresome as a teacher to keep repeating every word. H bond is just called an H bond. So you're going to hear me just call it ionic, H bond, dipole. And then the last one has several names. I call it London because that's the easiest one to call. The best part about this board is we made it so I don't have to stretch my arm and I can reach the top of the board. The other names that are shown in the notes, if you look at them, and it's up to you, you don't have to print them. You can always just pull them up on the screen and look at them later and ask me if you have questions. the name that the chemistry book that we used to use for years called it is induced dipole, induced dipole. And so what a lot of students will call these is the ID, so capital I, capital D for short. And so the idea is it's not a true dipole, it's a dipole that was forced to happen. And this happens in anything that is nonpolar. So we had ionic, we had polar, we had very polar, and we have nonpolar. So we covered all the categories here. I call them London usually because that's the simplest name rather than keep saying induced dipole. London is the first place. I would assume London College was where they were first hypothesized. They were truly called London dispersion forces because there's a dispersion that happens, and it was Dr. van der Waal. So that's why if you look on the notes, it has all these different names, and they all mean the same thing. And so I don't care which one you call it. It's more when I call it that you can recognize I'm saying the same thing. So I usually either go with London or induced dipole. And again, they repeat themselves because there's always has to be two things present. So the example I'm going to do for simplicity, and then we walk through lots of examples in the notes, is I'm going to do 2 argon atoms. And so everything has induced dipoles. And if you look at argon, you're like, well, there's nothing positive or negative about it. There's no negative or positive area, or in sodium chloride, the fullness. But there is, because at the very center of argon is that positive nucleus. And then you have these electrons that are orbiting it in whatever direction you want electrons to be moving. And that, what happens is this electron from the one particle, which could be an atom. So it can be an atom or a molecule, a nonpolar molecule. This electron has a momentary attraction. So this is a momentary, it's very momentary, like the smallest time frame you can imagine. So it's a momentary attraction between the nucleus and the electron. So the nucleus of one atom and an electron on another. So technically, these exist in everything, even in water. They're just so weak. These are extremely weak compared to the other ones because they're so momentary. That's why the term dispersion forces was actually a really good term for them, because they're just dispersed. The thing about them that's really cool is if you ever travel, and you get to travel somewhere where it's a warm climate. So when I was in Costa Rica, when I was in Thailand, those of you from Vietnam probably remember. So those lizards that are always climbing all over the walls. And so when I stayed in these places, and I loved them because they would sing. Some people freak out but they're like beautiful, but they're geckos and they can walk on the wall, and they didn't know why. And so there were different theories. So was it like Spider-Man? So Spider-Man actually had a gooey thing that was in his thing. So he made a web. But what they found, they look at the gecko's little paws under a microscope, and there's so much surface area. They have so many indentations that they have like this infinite number of induced dipoles. And if you get this huge amount of surface area, so once you increase the surface area, huge amounts of surface area, you increase the induced dipole, and it becomes much stronger. And so geckos, if you and I had so many indentations on our fingers, we could walk up the walls too. And so that's how geckos can walk up the walls. This step is only for induced dipole. It doesn't affect the other ones. So if you have two things, and we'll look at that as we go through the example, if you have two things that are nonpolar, you would look at size. So an example would be the noble gases. So if we were comparing argon to xenon, Xenon is much larger than argon. Xenon's going to actually have a higher intermolecular force. So it's going to have a much stronger intermolecular force because it has a much greater surface area, because size matters in the case of induced dipole. In the case of these top three, there's actually a positive and a negative area. And so the positive, the difference between the positive and negative can differentiate them. And so if we run into that, we'll look at that. And so that's what the rest of this page and the next 2 pages is. We just walk through a bunch of different examples. So before I erase with my squid hat, does anybody have questions? You guys can ask with the space bar. We're good? So much easier when I can see your whole person. All right. So the examples, and I'll write them out, and we'll walk through them one at a time, is we're comparing 2 different compounds. So CH4 versus silicon tetrafluoride. And the question wants to know which one has stronger intermolecular forces. So to figure that out, we have to put them in one of the categories. So first of all, it's not ionic. These are both nonpolar. So if you see only carbons and hydrogens, that was something that I talked about in the very first lecture. If you see only carbons and hydrogens, it is nonpolar. So instead of just saying nonpolar now, instead of saying hydrophobic, we would say it has London, or you can say induced dipole. So I will ask sometimes, what are the intermolecular forces? Silicon tetrafluoride is also nonpolar, and sometimes you're going to have to draw Lewis structures. This is why we had to do those first 3 weeks of just drawing structures and stuff. But the silicon would have, it's right under carbon, it makes 4 bonds, it loves to make 4 bonds, you could do your dots, and you would get that it's completely nonpolar. So although the fluorines pool, they all balance each other out, so it's also nonpolar, it is also going to be London. So if they're both London or they're both induced dipole, one of them always wins. So something always wins. It's never a tie. And the winner is going to be the SiF4, and it would be because it has a greater surface area. So if they're both London or both induced dipole, the one with the greater surface area. And there's a couple different ways. Sometimes it can be from looking at the molecule, but if you have your periodic table, silicon with 4 fluorines is definitely much larger than a carbon with 4 hydrogens. All right, the second one. So this is why we did all the stuff with polar, nonpolar, the organic chemistry stuff that Janae was asking about, was to get to this lecture. And this page is to get to the next page. And so the term kind of keeps building on itself. All right, so CH3NH2. And I think you guys can still see me. That's probably a little bit better, maybe? All right. Now, without drawing Lewis structures, you can usually get to your answer. And it is right here, the NH2. You see that? That is H bond. So again, whenever you see a hydrogen that's attached to NOF, N, O, or F, so the gnomes hats, they have them up there. I don't have a gnome hat, or else I'd be wearing it tonight. Then you have an H bond. And so we see a hydrogen attached to the nitrogen. These hydrogens are attached to the carbon. Again, this is why we did the organic chemistry, so you could interpret these. All right, this picture is not an H bond, because this hydrogen is way over there on the other side of the carbon, and this nitrogen's over here. But we do know that nitrogens are going to pool. So there is going to be a pool. It is definitely polar. And now instead of saying polar, we say dipole. So the type of intermolecular force is a dipole versus an H bond. And which one is stronger? It's back to the list at the top of the page. H bond. H bond always beats a dipole. It's an extreme dipole. All right, if you guys have a question, assuming you'll stop me and ask. All right, so the next one, CH3Cl versus cesium chloride. So this one's actually, you got a winner right off. Cesium and chloride are on two different sides of the periodic table. That is ionic. Ionic always wins. Now, it doesn't show up on this page. If you have two different ionics, there is a way you can compare them. And we'll get to that. Maybe not today. All right, we do want to do all the intermolecular forces just for practice. If you have a carbon, it's going to make 4 bonds. So this is a carbon with 3 hydrogens around it and a chlorine. And so that chlorine is going to pull. So this is definitely pulling towards the chlorine. So it is going to be a dipole. So polar things are dipoles. It is not an H bond because the hydrogens are not on there. But ionic always wins our contest. All right, I think I have room for one more. So CH3, CH2, CH3 is the first example, and then CH3, OCH3. And I'm assuming you guys can still see the board. Yeah. All right, this is only carbons and hydrogens. Anybody remember? Only carbon and hydrogen is nonpolar, but instead of saying nonpolar, you're now going to tell me the type of IMF. And again, you can say ID for induced dipole, or you would say London. I seem to be on a London kick today, so we'll go with that. All right, what happens on this one is we have that oxygen in the middle. This is the ether that we were talking about. And oxygens love to make these bends. We don't show the lone pair of electrons, but this is the one with the Mickey Mouse ears. And so you would really have these CH3s down here, and the oxygen is pulling up. This is a dipole. Now, the mistake most students will make on this, if they make a mistake, they will correctly get that the CH3, OCH3 beats this other one, which is propane. The mistake is they'll think it's an H bond, and it's not an H bond. It's not an H bond because this hydrogen is attached to the carbon. So organic chemistry, we write hydrogens after the atom that they're attached to. So this hydrogen is attached to the carbon. There is no hydrogen on the oxygen, so it's not an H bond. It's just a dipole. All right, and then the next one, I think you can still squat down. It's good for me. So this first one is just all carbons and hydrogens. So London. You can write nonpolar if that makes more sense to you, but if I do ask the type of intermolecular force, again, you would say London, or you can say ID for induced dipole. And the other one is interesting. I do this one always as an example with the class, is it's an isomer. These guys are isomers. They both have 4 carbons, and they both have 10 hydrogens. So this is also London. It's also nonpolar. It's only made up of carbons and hydrogens, but something always wins. And if they're both nonpolar, to pick the winner, do you remember? You have to pick the one that has more surface area. And so this is always fun in class, asking which one has more surface area, and half the people, everybody's guessing until the first time they see it. It is this first one. And that is because it's linear. It's not actually linear. It's going to be zigzags, if you remember, whereas this one would be like this. So the one over on the right forms into a little ball. The more strung out it is the way I talk about it, the more surface area. So surface area, if they're both nonpolar, you always look at surface area. And so for the answers, they were all the one on the right, and then this one's the one on the left. Oh, there is one more. We'll write the last one up here above the cesium. All right. I'm still getting used to, after 25 years teaching in the same classroom, I'm used to how much space I have, and so I'm learning this. All right, OH. As soon as you see OH, what do you say? And they all said H bond. So you see an OH, this is an H bond, but before you circle it, you want to look at the other one. And a comment I made just a few moments ago was that H's are always written after what they're attached to. There is one exception, and that is often when things are written all the way on the left side of a molecule. That is an H bond. So the HO is an H bond, and the O is an H bond. So this is a double H bond. And so 2 is always better than 1. So the double H bond wins. And that's when I ask for you to explain why, and I say give an explanation, that's all I want you to say. I don't need you to write a full sentence or anything. You can just say H bond, double H bond, and circle the one that's a double H bond. That's it. You're done. And so before I move with the little water droplet to the next page, did you guys all connect your things at the top, the solid, liquid, gas? I'll give you a hint. The snowman at the top of the page, I know Edward doesn't have his notes, but the snowman would connect to the ice cube because they're both solids. So that's what makes them special. But is there questions? You guys can always just push your space bar down and it will hopefully ask the question.
I have a question.
Go ahead.
So go back to, I guess this would probably be any of them, but you said that the bottom one that we did where you said, look at the surface.
Yeah, that's only if they're both London dispersion. They're only if they're both nonpolar. And if they come out with the same number of carbons and hydrogen, so basically you're usually on that one, it's going to be more like the very first one, Janae, where you can look at the molecular weight on the periodic table, that the SiF4 is much larger on the periodic table than carbon hydrogen. So this one has a much greater molecular weight, which means it has more surface area. This is very rare that you're going to see two things that are isomers, but I did put it on there, so it was one we did together. And so if you see two things that are isomers, you're going to pick the one that is longer. So once they start having these side groups, it compacts them in and they have less surface area.
Okay, and then also I can't really see the, your writing in the right corner up on top where you just got finished. What is that saying?
Oh, double H bond.
Double H bond.
So this is one H bond, this was two H bonds. So if you, the more H bonds you have, the higher the intermolecular force. Yeah, really good questions, thank you. Anybody else, questions before I erase and move to the next page? All right, so I'm gonna flip pages. I'm gonna erase with the squid hat and I also have to open a window, so hold on. So if it gets noisy, I'll close that. All right, so what we're going to do with these are different properties of liquids. So the lecture tonight is about liquids. Next week, we're going to talk about gases. And gas is really unique because it's all math and stuff. But there are 6 properties of liquids that we're going to walk through. And the first 2 go together. They always go together. So VP is vapor pressure. So you'll usually just see me write it as VP. And the second one, I'm going to leave a little space. There's a space in your notes, is BP, which is not blood pressure. I had a student one time, and I went through this whole lecture, and they're like, yeah, I'm writing boiling pressure, boiling point. They're like, I understand all this stuff that you just went through, but I don't understand what blood pressure has to do with anything. And so it's kind of keeping in context. We're not in an anatomy or nursing class. We're in a chemistry class. So vapor pressure is, vapor is a term for gas above a liquid. So if you in the morning make a cup of tea or a cup of coffee, you'll see, or just even hot water, there'll be vapor coming off of it. And so we call that water vapor. Pressure is something we talk about much more next week. Pressure is collisions of particles, collisions of the gas. So if you increase the amount of gas, you're going to increase the pressure because you're going to have more collisions. So the way you increase vapor pressure is you got to have, the big thing that makes a gas different, I should have rearranged these notes. A gas has no intermolecular forces. So that is what makes a gas special. So these 3 weeks of lecture go all together, the solids, the liquids, and the gases. So we walk through the 3 states of matter. And so a gas has very weak intermolecular forces. And that's why they're a gas. So gases have escaped. They have no attraction. So if they have weak intermolecular forces, it's like, I'm free, I can do anything I want. So I used to give the example that while you're in class, like while I'm lecturing, you're all like a solid because we're all in a regular pattern. Everybody has their like seat that they sit in. There might be a little bit of jiggling, but not much. And then we take a break. And so you're kind of like a liquid. So there's a little bit of flowing, but you don't go far because you know I'm going to lecture again. And so people are moving around, but you're staying close. And then when class is over, we're all like gases. So we disperse and go far apart. So what it has to do with this is called a liquid property. This is the amount of vapor that has escaped. So how much has escaped? Let's add to this, escape the liquid. The more that escapes, the higher the vapor pressure. So the question really is, we're comparing strong and weak intermolecular forces. So you always go back and you figure out which one is stronger, which one's weaker. Is you're going to increase the vapor pressure as you decrease the intermolecular forces. And that is, again, because more escapes. The intermolecular forces are what holds it together, what holds the liquid, what keeps the liquid in there. And then as they escape, they become the vapor above, and we can actually measure that with a pressure gauge. So what boiling point is, and why I teach these two together is, oh, and there's my typo. I knew there was a typo in these notes, and I knew I'd find it as soon as I started teaching. Boiling point is the temperature at which the liquid turns into a gas. And it has to do with when the vapor pressure equals the atmospheric pressure. So boiling point changes as the vapor pressure changes. So we all know that water has a boiling point of 100 degrees Celsius. It turns out it doesn't. It only is going to be 100 degrees Celsius on a perfect day at sea level. So if you go and climb Mount Everest, which is not going to happen to me because I don't do great at altitude, but let's say we go on a class trip and we go and climb Mount Rainier. So Mount Rainier is 14,400 feet. The boiling point of our water is going to be like around 80 degrees if we try and boil a cup of water. That would be a great lab. I wonder if we'd be allowed to go. Probably not. I don't know. On top of Mount Everest, water boils at like 62 degrees, so you can't actually cook an egg once you get into what's called the death zone, which is where humans can't breathe very well. All right, So boiling point has to do with temperature. And I talk about this with gas laws next week. Temperature has to do with kinetic energy. So KE is kinetic energy. So if you want to be really sciencey, you talk about as kinetic energy. As you increase the temperature, you increase the kinetic energy. Kinetic energy is the energy of movement. So as you get more movement happening, you get of the particles. So this is chemistry. So we're talking about the atoms, movement of the atoms. And so you can always say that. The way I say it is you increase the jiggles and the wiggles and the giggles. So if you're giggling and jiggling, and so as you have more jiggles and wiggles, I think this is why it says on the syllabus, we're going to talk about jiggles and wiggles. So as you increase the temperature, it's actually, as the atoms get more and more jiggles and wiggles, they're going to increase the temperature. I'm right under the flight pattern for the airport, and this is time of day when all the FedEx planes fly over, so you're all going to get it here. They come in at a much lower landing, and so it's quite joyous because there's not as many planes as there usually are. All right, so boiling point is going to go up as you have higher IMF. And so as things are being held together, you're going to have to jiggle and wiggle more to overcome the IMF. So you're really holding on to something tight, like an H bond. You're going to require a much higher temperature, much more wiggles to let it go. You cannot jiggle apart a covalent bond. So a covalent bond, your arm is attached to your shoulder. You can't jiggle it apart no matter how hard you try. So Janae will know this because she probably played this when she was a little kid. There's a game called Red Rover, and all the kids hold hands and somebody tries to run through and break through. And so you can break through and the hands will release. That's like the hydrogen bond. But you never see a kid pull another kid's arm off their shoulder. That's not going to happen. That's like the covalent bond doesn't break with jiggles and wiggles. So going back to our intermolecular forces, the examples I have on the page are HBr and HF. So for HF, this is an H bond. You see a hydrogen attached to NO or F, hydrogen and fluorine, this is the strongest H bond there can be because fluorine's the greediest. So this is stronger, higher IMF. Just to make sure we get this complete, HBr is very polar also. The bromines, everything's always pulling on the hydrogen. So it is a dipole. But the H bond is going to win. Now, in terms of vapor pressure and boiling point, the HF is going to have the highest boiling point, and the HBr is going to have the higher vapor pressure. So they're an inverse relationship, and we're going to look at that with the graph that is on that page. So the typo that's in your notes, for those of you who have your notes, under vapor pressure, it says which has the higher boiling point. That should say which has the higher vapor pressure. And so that will probably make more sense. All right, and then it asks comparing fluorine versus bromine. And Janae, this is back to the question you had asked on the previous page. Now, both of these are diatomics. And when something is a diatomic, it's partnered with its twin, its identical twin. And so they don't pull on each other. These are both nonpolar. And so the term we use now is either induced dipole or we say they're both London. So if they're both London or induced dipole, again, pick one way or the other and just be consistent with it. What we look at, we don't look at electronegativity because there's no pulling going on. We look at size. And the bromine has a higher IMF because it's bigger. It has a greater surface area. On the periodic table, it's 2 rows below the fluorine. So in terms of what we just talked about, fluorine has the higher vapor pressure because it's the weaker IMF, and bromine will have the higher boiling point. And so when you get to next week's homework set, there's a lot of questions with these, either asking IMF or asking vapor pressure, asking boiling point. So if it asks about one of the properties, you always go back first to the IMF, and then you can pick your property from that. So now I want to go back and look at the chart, and it's a vapor pressure chart, but the two are related. The squid hat works beautifully. All right. So our graph. I'm just going to make a rough graph. This is, actually, I don't need to write all that word. This is the ether. It says diethyl ether. And then we have the alcohol. And so again, Janae, back to the question you had asked earlier in office hours. It's more when you see these words like ethyl alcohol, you don't really need to remember what the ethyl means. It means there were two carbons. I'm just making a way that we can label these. What we're looking at is more with these properties. So that's H2O water. And then there is actually one down here, which is glycol. And the axes are temperature and pressure. Oh, vapor pressure. All right, what these are is called vapor pressure curves. And what this line is here, this is the boiling point of ether at different, the temperature is the boiling point. So if we came up from any place, where it hits that line and we come over, this would be the atmospheric pressure. It's going to tell you when it boils. So like if we came up at 20 degrees, and for those of you who have the chart, you come up, and for the diethyl ether, it looks like it's around 450 degrees. So just as an example, this is going to be around 400, sorry, not 450 degrees, 450 millitorr. The units for pressure, we're going to talk about next week when we do gases. Again, I changed the order of stuff because I did the things that I wanted to do in person towards the end in the hopes. I wrote the syllabus before we went into this complete hibernation for extended times. All right, so these are the boiling points. And let's just look at 450 torr. If you come across, it does hit each line. So 450 torr, I have to think for a moment. That's about the pressure on top of Mount Rainier. It actually might be a little bit lower than that. It might be 400. But let's pretend like it's around 450. Maybe we didn't quite make it to the top. So if you come over from 450, and where you would hit like the ethyl alcohol, it would be, its boiling point's going to be, so this one was 20-ish degrees for the ether. For the alcohol at 450, we're at like 64, 65. As long as you're in the ballpark. And for water, it's going to be, yeah, like 85, 86 or so. And so this is saying if you were on top of Mount Rainier and you were going to cook something, you actually can't, you have to cook it longer because the temperature of the water actually doesn't get hot enough. So on top of Mount Everest, the pressure is 200 torr. So if you go down and look on the graph at 200 and you come across to the water, it is at 200 torr, which is Mount Everest. There is that much less. So pressure is how much oxygen. Since there is a quarter the amount of oxygen pressure as there is here, there's not enough pressure to push the oxygen into your lungs. So you don't, there's so much fewer oxygen molecules. So you're like gasping trying to find them. But the thing that's fascinating is the boiling point of the water is much lower. It's like 62 degrees. And so you can't actually boil an egg. You have to get to 65 degrees Celsius to boil an egg. You can't make ramen noodles. You can make hot chocolate really fast, but it's not really hot. It's only 62 degrees. And so the water actually boils a lot faster. It's just, you don't have to worry about purifying it, because once you're that high up, it's definitely pure because nothing's going to live up there. The ethylene glycol is the lowest. So you'll see questions in your homework where it's going to ask you to, it's going to ask questions about the graph. In all honesty, most of you will never have to do a vapor pressure graph again in your life, but you're all going to have to interpret graphs in some way. And so it's actually really good practice. One of the biggest questions that's usually asked about these graphs is which one has the strongest intermolecular forces. And so as you move this way, their boiling points are increasing at a given vapor pressure. So as we increase the vapor pressure, of course, things have more jiggles, and so their boiling points go up. But at this given pressure, the glycol is going to be our strongest IMF. It actually is so strong, it doesn't even, you don't even see the whole curve of it. So usually I pick ones where we just have two things, or they're really obvious to see the pieces on the curve. The other question that you will often see on this graph is, let's say we pick a point of 40 degrees Celsius and 400 torr. So my star here is 40 degrees Celsius and 400 torr. And the question would ask, when you're at that point on the graph, where between the ether and the alcohol, it would ask you what state of matter you have. So if this is the boiling point, boiling means you're changing a liquid into a gas. The ether has already crossed over. So the ether has already boiled. It's a gas. So that's my G. The alcohol hasn't made it to its curve yet, so it's still a liquid. The water would still be a liquid. The glycol would still be a liquid. None of them have made it to the point of boiling. And so these are read that you're at a specific vapor pressure. So you're on Everest, you're on Mount Rainier. Where we are here in Gresham, we're pretty much at sea level. And so sea level, or you can say, I can't say Mount Hood Community College because none of us are there, but it is 760 torr. So you'll often see questions that will ask, what is the normal boiling point? Normal means, okay, we're all at sea level. And I think the terminology comes that a lot of the original people who worked with this, with gas laws and stuff, were in Italy, like in Sicily. So they were in the Mediterranean areas that are at sea level, and the Greeks and stuff. So if it asks you what's the normal boiling point, and that's what, if you have the graph in front of you, you can see, or when you look at it, there's a bold line going across at 760, and it even says normal boiling point. All right, questions with either of those? If not, I'm going to erase it. And again, it's just more interpreting, and it's when you do the homework. I anticipate next week there might be more questions with the homework. I don't know. Do the homework and then look at the things. And you can always also email me. So there's one more on this page, one more property. And this is where it's nice to be at school, because I have those two huge boards and I can fit 2 pages of notes on the 2 boards. All right. The one at the bottom of the page is enthalpy of vaporization. All right, I did not anticipate this. I forgot this is my smallest room in the house. And so it's really warm in here because I have all the doors, everything closed. So it's just like when I'm lecturing, I'm up there under all the spotlights and stuff. So enthalpy of vaporization, does anybody remember that term enthalpy? We saw it last term. It's a Greek word. And it means heat. So it's the amount of heat, and vaporization means to vaporize. So liquid to a gas is vaporization. So enthalpy of vaporization is the amount of heat. So the amount of heat to change a liquid to a gas. So the only question I ever get with this is really, what's the difference between heat and temperature? I would tell you to Google. They'll give you a much better answer than I can. And I always read the answer and I go, oh, okay, that's fascinating. And then I can't ever remember it to be able to explain it. What I would tell you though is heat also has to do with jiggles. So if you want, you can decide this one has to do with wiggles and the other one has to do with jiggles. But as you increase your intermolecular forces, you're going to need a lot more heat to overcome the attraction. So you're going to increase your enthalpy of vaporization. So it's a similar idea as boiling point. It's just boiling point measures temperature, which is degrees Celsius, and heat is measured in kilojoules. You could also do joules. And so if we were comparing our examples like up above, you're always going to pick the one with the stronger IMF. Now, this has its own heating curve type of thing. And so I don't know why they call it a heating curve, because it doesn't curve at all. It's a staircase. And it makes these steps. So these flat lines are actually important. So again, and it's a little bit different. So this time the y-axis is temperature, and your x-axis down here is heat or enthalpy. So as we're adding heat, what's going to happen, this point here, we're at the flat line, this is the melting point. So MP is not military police, don't worry, nobody's coming after us. But, and then this flat line would be the boiling point. And with these are not straight up and down. It's not that I can't draw a line, they're diagonal. This is when you're a solid. So at a low temperature, you're a solid, and as you're adding heat, it's still ice. Let's think of it as water. It's still ice until you hit the melting point. And what's happening here when you're at the melting point is both the solid and liquid exist. So if you make, like, let's say you like lemonade or iced tea, and you make that drink and you add the ice cubes, it will be at the melting point of water, which is, well, it would be different because it's lemonade. Let's say you have just water. If you have both the ice and the water present, you're at 0 degrees. Once all the ice melts, you're here, and now it's in the liquid state. So that's my L for liquid. And so you heat it up, you keep adding heat, heat, more heat, until it hits here. And then while you're here at the boiling point, so think of a pot of water on your stove, it's both the liquid and the gas are there. Most of us take the lid off our pot, and so the gas is dispersing and escaping because it has enough jiggles and wiggles from the heat. And eventually gets to this point where, like, you got a phone call and you boiled away the whole pot, and now you're gonna set the smoke detector off. So it's all escaped and it's flying away. These two flat lines have a name. The one between a liquid and a gas is called delta H of VAP. So VAP, and that is the symbol for this one up here. So delta H VAP. It's hard to read there because I have to write really small. So delta H is our symbol for enthalpy. And if you remember when you learned about enthalpy back in 221, you can't actually ever know the enthalpy or the heat of something. You can only know the change in it. And so that's delta H is change. And the VAP just is for vaporization. The other flat line between the solid and liquid, that is a triangle H. And then this is fusion. So this is all looked at from the perspective of the liquid. So going from the liquid to the solid, we would call it as fusion. Going from the liquid to gas, it's called vaporization. So it turns out it's all about the liquid. And then you'll be given these numbers. And we're going to go through a practice math one. But this is the idea that you're heating it up. You have a solid. Up to this point, you have a solid and liquid until you added enough heat to overcome this. And then you're a liquid in this whole space between the melting point and boiling point. So the example we're going to do here is going to be for water. when you do, there's 2 in the homework and 1 on the worksheet and stuff for next week. You'll have to fill in this part of the curve. This graph will always look the same. It's just the numbers that you're going to fill in are going to be different. There is a question though before I go on, and it is this line here is longer. The delta H of vaporization is always much larger than the delta H of fusion. And that is, vaporization is the liquid to gas. And to change a liquid to a gas, you have to overcome, you have to wiggle apart, you have to overcome all the IMFs. So you have to wiggle them apart. So what's the difference between a liquid and a solid? Well, a solid just means you're going from flow, which is a liquid, and a solid means you have a pattern. So the solids, like we just did on the homework tonight, they all have like a specific pattern. Once you melt them and turn them into a liquid, they start flowing and you lose that pattern. They both still have intermolecular forces. And so delta H's of fusion are not usually very large numbers compared to delta H's of vaporization. In terms of water, it's a huge difference, and that's because water has H bonds, and H bonds in water are very significant. All right, so we're gonna fill some numbers in. If this is water, this is 0 degrees for the melting point, and the boiling point is 100 degrees. So I recommend filling those in, and then if we go and look at the example, it says we're going to deal with 50 grams of H2O, and we're starting at 40 degrees, so we're starting somewhere here at 40 degrees, and we're going until it becomes a gas. So on the curve here, we're starting around here at 40 degrees. And it says go until it becomes a vapor. This corner right here is where it's finally a vapor, meaning it's a gas. It's completely changed to a gas. So to do this math, we're going to have 2 steps. We have to change the liquid to the point of delta H vaporization. So I'm just going to write here liquid. And then we have to go all the way across this line here, the delta H of vaporization. And the question wants to know how much heat to do those 2 steps. So I'm going to show them as 2 separate steps, and then we add them together. So you can do it as one long thing. The key, and those of you who've had me, which is the vast majority of the class, you need to label this calculation carefully. That would probably be the only points people miss on a question like this. So the chart has numbers for you to figure out, like the delta H of vaporization. We'll do this one first. If you look up above, it's 40.6, and then it's kilojoules per mole. So rather than memorizing a formula, the key is that we're solving for how much heat, which means we want just kilojoules. It means we have to get rid of the mole. Well, the other thing we know is we have water. And so to get rid of the water, you use your periodic table. I realize that's the other thing I'm missing here. And so you would add up the 2 hydrogens and the oxygen, and it's 18-ish grams, 18.016 grams per mole. So for our factor label, my grams of the water will have to be on the bottom. And then to get rid of the grams, it told you in the problem that you have 50 grams. And then there's nothing here. I did the problem backwards because that makes more sense to me that way. And then we'd punch it in your calculator. When we were in class, you guys would all punch it in. I did it before while you guys were doing other problems. And you get around 113. Now again, if you punch this in and you get 112, 114, we're in the same ballpark. So that's the second step, the delta H of vaporization. So going back up to the liquid step. So if we look at the little chart on the side, it gave us delta H of vap, delta H of fusion, and then it gives you these C's. the C of the liquid, it just puts a question mark because I'm seeing if anybody remembers anything from 221. This was the 4.184. Do you remember that number? Some of you are going, oh yeah, 4.184. Do you remember the units? This is, we're up to, it's joules per gram Kelvin, or we're gonna leave the Kelvin out for right now. We're gonna talk about Kelvin next week, because when we do gas laws, that's the purpose of Kelvin. But this is the number, this would be given to you if it was anything other than water. So this is our first step, this is our second step, but we have to get it to kilojoules so we can add these two together. So we gotta get rid of the grams. Oh, we know it's 50 grams. All right. So 50.0 grams. Nothing underneath. We'll just put our heart. We have to get rid of the Celsius. And it's going to be 60 degrees. It's not 40 degrees, because 40 degrees is the temperature you start at. And you might remember this is mass times change in temperature times C. It's a change in temperature, and that's what's happening here. This is going from 40 degrees to 100 degrees. So it's a 60-degree change. So whenever you're on one of these diagonal lines, the solid, the liquid, or the gas, it's not the temperature you're at, it's how much the temperature changes. So our Celsius is going to cancel, and then we have to get the joules to cancel. And I do these always in kilojoules. Maybe since I'm recording it, maybe you'll all do it in kilojoules. If you do it in joules, that's fine as long as you show your unit. The kilojoules, just make them nice smaller numbers. So you would punch that in, and again, I did this before while you guys were working on stuff, and I got 12.6 kilojoules. I just went with 3 sig figs, because I think all my numbers had 3 sig figs in the problem. And then you add together. You just add these two steps up. So we add our two numbers up, and you get my answer, which is 125. So 125, 126, we're in the same ballpark. And I actually did it all in one step in my calculator, so that's why I got 125, and then I rounded on the board to 3 sig figs. So again, if you got 126, it's the same answer, and kilojoules. And just a reminder, the K is small for kilo, and the J is capital for joules. But that's actually the only math you're gonna see this next homework set for next week, which is a lot easier than the solid stuff. But I think you guys will do pretty good with the solid stuff. And again, the office hours this week on Thursday, we can focus on the lab. You're all going to have the same numbers, and you can see how well the gnomes did. The gnomes did actually quite well. All right, is there questions before we go to the next page? I'm going to start erasing over there. If you have a question, just push down your space bar.
Dr. Sherpa, I just wanted to make sure that the last answer we did, it was 1,000. Is that 1,000 joules? Over.
Oh, 1 kilojoule over 1,000 joules. That's just to get us to kilojoules.
Okay.
So you're talking about that number down there. Yeah, that's what kilo means. You guys ready? All right. I have. Now I can see Aaron. There was so I'm on the next page, which I've noticed my page numbers are really bizarre on everything because I changed the order and I didn't change page numbers. But not surface area. I'm so sorry. surface tension. Actually, that was a good mistake. And that is because it's not the same thing as surface area. And it is a mistake that a lot of students make. So I made it for you, so hopefully you won't. So surface area was when we talked about what was on the board down here previously, the molecules that had like the side groups, they had smaller surface area. That's based on the size of them. Surface tension is the idea that, so if we have a glass or some kind of a beaker of molecules on the surface. Yes.
Looks like you, I don't know if it's on my camera or what I'm watching, but you look very blurry.
Mine too.
Yeah, me too. Me too.
I don't know why I did that. It should focus in a minute.
Oh, I can't see it.
Bump it. I don't know why I did that. Did it focus again? No. Why is it doing that? I wonder if I turn it off. Oh, it did this when I was at school. And asked Joey. I don't know why I did that suddenly. I wonder if it got darker. I can call Joey unless somebody knows why a camera does that. Talk it through. Joey. Yeah, he's probably not going to be able to help. Let's keep going and see if it comes back in. Maybe I'll erase the board and see if it comes back in. Maybe it's because the sun is setting. There was a solar flare.
I'm wondering, would turning off the light and turning it back on work?
I can't see anything. We could go, it's a cloudy night. We can't go look at the stars. I don't know. Oh,
I think it worked.
you know why I can't tell? Because I have my glasses off and everything's just blurry. So it was like, for the past 5 minutes, you all got to see what my life, any of you who don't wear glasses got to see what those of us who wear glasses, what it's like all the time. All right, great idea there, Erin, thank you. So surface tension is the surface molecules, which would be all over the surface. They obviously have an attraction for each other, and they also have an attraction for all the molecules that are down here within the solution. And so that creates, I went out of focus again, didn't I? You guys will have to tell me, I can't.
You're good.
I'm good? Okay, that this attraction creates a tension across the liquid. So the higher the IMF, the higher the surface tension. So the greater this attraction, the more it is. And so they call them, like here in Oregon, I think my students call them the water skeeters. They're those bugs that walk on the water. You see them in the summertime on the water. And they can do that. This is actually going to be the bonus. So it was a question, a couple of you have been asking me, is there going to be any extra credit? There is. I teach a kids class, as I've mentioned to many of you, and I actually found these labs. It was really cool. So I used to teach it over at a church that was here on Mondays, and it was a Sunday night, and I had some of my former students came over, and I said, I have to do this kids class tomorrow, and I don't know what I'm doing. It's in 12 hours, and I have 17 kids. And this one guy said, well, why don't you do drops of water on a penny? And I just looked at him, and I'm like, what can I had them for an hour. But it's actually really cool. It has to do with surface tension, that if you have a penny, just a regular penny, a 1 cent piece, and droppers, and you see how many drops of water you can get on the surface of a penny, and it's a lot. The record I have is like, it's over 100 one of my students got using a regular dropper. Some of you aren't going to be able to do that challenge because you don't have a dropper, but the other thing that's really cool is bubbles. So it's bubble season. So you can go and play with bubbles. Right? I don't know if you can see the bubbles, but you can see if you can catch them and make, I can't, but making bubbles and stuff. So we make these, we have bubble wands, we make huge bubble wands. So this was like a question, Megan had sent me an email, she teaches a summer camp. And so there's all these challenges I do with the kids. And so I was gonna record my PowerPoint, which gives you what the challenges are. And if you wanted to try them at home, you would actually have to take a picture of yourself if you succeed. And you would have to be in the picture to show that you were successful. So if you want, you can try it. You have until the midterm. But so surface tension is really cool. And so it's why those bugs can walk on water. And so the one challenge is something that I can't do. I've never been able to do it. You can actually get paper clips to float on water. And the reason I don't get it to work is your finger cannot touch the water. So your finger has, we have lots of stuff on our hands, but there's surfactants on there. And if you touch the water, you disrupt the surface tension because you disrupt the attractive forces. So they become attracted to your finger for a moment and you lose that surface tension. So it has to be somebody who's really, you have to be really focused. It's actually really wonderful. Janae might love it because kids get really quiet because they're trying very quietly to get it to work, and they usually can. The other thing that's really cool is there's this really cool demo, and you shake pepper, like, you know, salt and pepper. So pepper's brown, and you put it on water, and so of course it's floating, and then you add 1 drop of soap, and all the pepper just goes to the side, like in a moment. And the reason for that is the soap interferes again with all the water attractive forces. And so suddenly the pepper can't be on there and it gets pushed to the side. So it's kind of cool. And so it is why, like, you can buy bubble wands that are hearts in all different shapes, but a bubble is always spherical when it comes out, and it has to do with the surface tension pulls it into the smallest surface area. All right, so the higher the IMF, the higher the surface tension. All right, the next one is viscosity, and this is actually really cool. So the picture on the page, viscosity, I'm gonna put this in quotes because I don't like this definition. This is what you will get in the book. It is called resistance to flow. And students will write that. And so that's why a lot of things will say, give it to me in your own words. Viscosity, what I think of it is as stickiness. Well, see, now you can hear all the birdies as the sun is setting. And now my neighbors are playing music for us. All right, so viscosity is things are sticky. So if you think of something like honey, honey is very viscous if you get real honey, not the fake stuff. The high fructose corn syrup is also viscous. It's not the best example here because those are mixtures, but the most viscous substance that there is pitch. And so if you have the notes, or when you look at the notes, there's a picture there. And it was this scientist back like over 100 years ago. And it takes 8 years for 1 drop to fall from this. This is actually in New Zealand, and they actually have a live camera on it now. And I think it was 4 or 5 years ago, a drop fell during my lecture for 222. It was that week. And you could watch it live on those gaming. Joey was in high school, and so he gamed. And they would cut to it during the games and say, it's about to drop, it's about to drop, but it looked just like this. It will look just like this for years, and then suddenly the drop falls. But obviously, if something's sticky, the higher the IMF, the greater the attraction, the stickier it's going to be. The other way I talk about is resistance to flow. So the liquid is all about flow. Liquids want to flow. And so if you have a high attraction, a high IMF, you're not going to flow. You're kind of, so it's kind of like when you're walking along and you're talking and you see somebody you know or you're attracted to, you're not going to flow. You're going to kind of be attracted to them and you're not going to want to keep moving on. All right. the very last one, and there's a reason I do these in the order that I have done in your notes, is the last one is called volatility. And Janae might like this one because she has a degree in psychology, and so her, you know, when she hears the word volatile, she's probably thinking somebody who gets angry really quickly, has a lot of emotions. In fact, today I was trying to look for a picture for this, and I'm always amused. That's why there's that emoticon who's very volatile, so he gets angry really quick. In terms of chemistry, I have to put the word volatility for chemists. If we're thinking of states of matter, what state of matter would be the most volatile? Would be a gas. Gases are volatile because they're all about chaos. They're moving around. Liquids are flowing, but they're flowing very calmly. Think of a stream, right? You think of it, oh, it's very calm as it's flowing by. So volatility is ease to change, ease of a liquid to become a gas. So the easier it is for something to change, to evaporate, right? The term for liquid to gas is to evaporate. The easier it is for something to evaporate, the more volatile it is. So we're going to see, I'm going to do it this way. You're going to see, as you increase the intermolecular forces, it doesn't want to leave. It doesn't want to escape. So you're going to see a decrease in volatility. So these are opposite. So the very first one we did, vapor pressure, the vapor pressure and intermolecular forces were opposite. So the stronger intermolecular force would have the lower vapor pressure. And then the last property I talked about, volatility, because both vapor pressure and volatility are looking at something becoming the gas. You want it to escape. So how easy is it for it to escape? It's 4 in the middle, so the boiling point, the heat of vaporization, surface tension, and viscosity. As you increase the intermolecular force, those properties increase. And so there's an example at the bottom of the page, and we'll look at that. This is so awesome. It's just like being in class, and this has a typo. I love it. So none of you will probably notice my typo, so I'm going to go along with it. So we're comparing these two. And when you're comparing these two, as soon as you see an NH, if you get nothing else from this whole lecture, from this whole next week, when you see NOF, when you see a hydrogen attached to NO or F, you want to go, hey, that's an H bond. This is huge in biology and biochemistry. So DNA, so actually this is a good example. DNA is held together by H bonds. So DNA is 2 strands. And the 2 strands are held together by an H bond. The backbone, these strands are covalently bonded within them, so the whole strand. And this is actually really important. So it's like a zipper. So you can pull the 2 strands apart by the H bond, but the strand itself doesn't come apart. And this was the genius, whatever your opinion or whatever my opinion is, of James Watson, who won the Nobel Prize for DNA structure. They were brilliant, and the brilliance of them and why they deserve the Nobel Prize is the H bond. That they said there must be an H bond, and that H bond says that these 2 strands can easily come apart and easily come back together. You don't need enzymes or something. So to do a covalent bond, like to get your arm off, you would have to have a chainsaw. And but to like open a zipper, you just need a little bit of friction. All right, so NH3 has H bonds. This one, we have something other than just carbons and hydrogens. So it's going to be a dipole. It's probably a really weak dipole, but it is a dipole. And so then the question, so this is an H bond. So that has the higher IMF. So whenever you're asked these questions, I'm going to erase my DNA. You want to look at your type of intermolecular force to figure out which one's stronger, which is our NH, the one with the NH. And then you look at what the question asks. Which one of these is a higher surface tension? Well, surface tension is tension. It is a higher IMF. So my NH3 is the higher surface tension. And again, the typo here is it should say NH2, but we don't need to worry about it. And then the second question says, which one has the greater vapor pressure? Well, vapor pressure is the one that can escape to become a vapor. And so the weaker one is the higher vapor pressure. So again, vapor pressure and volatility are how easy you can escape. So you always pick the weaker one. A question that always comes up with this is how it's worded. It says, which has the greater vapor pressure at 20 degrees? That goes back to the vapor pressure curve that we talked about. Vapor pressure always changes with temperature. So as you increase the temperature, you have more jiggles, so more is escaping. So you'll usually see it say at a specific temperature. You can kind of ignore that. All right, the second example is C6H12 and C10H22. All right. So you see only carbons and hydrogens. If it's only carbons and hydrogens, you're going, that's nonpolar. So again, Janae, back to the question you asked me during office hours was really important. This is one of the big points of the organic chemistry. You see compounds with carbons, hydrogens, you're thinking nonpolar, hydrophobic. And then today, in terms of what we're talking about for intermolecular forces, we're going to call it either London or induced dipole, ID. Again, I don't care which way you go. I don't remember what I called it in the homework. So these are both London. They're the same thing. We have to pick a winner though. So which one has the stronger IMF? If they're both London, and again, you only do this if they're both London, you always pick the bigger one. And this one, 10 carbons is more than 6, so this one has the higher IMF. Now I'm not circling it yet because now we have to read more. So you figure out, is it polar, non-polar, is it an H bond, pick the higher IMF, and then we can go to the next question. So it asks, which one's more volatile? Well, the volatility is how easily it escapes. So the weaker one always wins, the volatility. So the C6H12 is the more volatile. And then it asks, which is more viscous? So viscosity is stickiness. Think of honey. Honey is delicious. Honey is amazing for you. So the winner of the IMF wins the viscosity. I think the hardest thing students have with this is 3 of the 6 terms all start with a V, and that sometimes in their brain gets mixed up. You guys have a huge advantage, which is you get your notes. And so as long as you write your notes out really nice so you can follow along, because again, your next midterm, you are gonna have a limited time. So I would make sure you approach it with your notes nicely done so you can follow along, or that you're actually studied. I think I only one time in my life had an open book test. I don't actually like them as a student. And so I wrote my notes. I had and I knew exactly where everything was in my notes, but in preparing my notes, I never actually looked at them during the test. And so it was like a 4-hour exam, and I did it in a half hour, and I got 100%. And everybody else is there flipping through their notes, and things are falling all over the place, and yeah, it wasn't pretty. So I would approach it that you have them there as a backup. Is there questions before we go? We just got one more page.
I have one.
For practice, go ahead.
I was wondering, what do you have written above a CH3, PH3? There's a little light spot.
Vapor pressure, VP.
Oh, VP. Okay, cool.
Yeah, I think that's why I don't like the dry erase. I like the chalkboard better, but yeah. Anybody else? Questions? So we're gonna do one more page. I don't know what time it is. Does anybody know what time it is?
It's 8:30 for you guys.
Okay, thank you. My computer turns off at 9 o'clock. I was having a lot of trouble the first 2 weeks of the term with sleep. And I realized that Joey had we got a new Wi-Fi, like one of those super duper Wi-Fis. and it was messing up my sleep. So it's programmed, it goes off at 9 o'clock. It goes to sleep, and my sleep just became complete bliss again. So I pondered this because a lot of you are really young and you've just always grown up with all this Wi-Fi stuff going through you, and so you've probably never had a normal sleep. And so that's why you should not sleep with your phone. Your phone should be turned off at night, and even alarm clocks, all that stuff. Nothing should be around you. You should allow yourself to be like out in the woods, like Aaron when you get to sleep in that fire tower. The last 2 pages are the practice for the quiz, and I was just going to videotape them because I would like you guys to try them, but we can see. I think we'll do, if you have the notes or when you get to print the notes, Edward, we have this huge box of paper here. You could always, I think we only live like a mile from you. If you get desperate and need paper, we got tons of it. Anyway, there's a connect the dots, so you can try the connect the dots. I won't ruin what the shapes are, but the first thing I need to do before I forget is they are going to be a solid, a liquid, and a gas. So again, the theme of the second midterm is the 3 states of matter, and so I want to go through the terms and also what makes each one of them special in terms of dihydrogen monoxide, in terms of water. So the word for a solid becoming a liquid is, of course, melting. And we talk about the temperature that happens, that's melting point. And then a liquid becoming a gas, that would either be boiling or evaporating or vaporizing. It doesn't matter to me. You can Google, you know, there's people who sit there and say, well, they have different meanings, and I understand, but it really doesn't matter in the big picture of it all. All right, if you go back from a gas to a liquid, this is condensation. So I know Janae gets up really early in the morning, and I do too, and so you often will see condensation happening. And so that's the water vapor in the air because it's still very cool in the mornings. It's one of my favorite times of the year. And so the water vapor in the air, you see it condensing. All right, and a liquid back to a solid is, of course, called freezing. Some people will say solidifying, same idea. And so you guys know those terms, but just to make sure, is you can also skip the liquid state. So if the pressure and the temperature are just right, this is why dry ice is called dry ice, because it never becomes wet, it never becomes a liquid. And that is the word that starts with an S, so that is sublimation. And again, it's more being familiar with it. So as I said, you have your notes, but you want to be familiar so you're not trying to look through. A gas skipping the liquid state is when it snows, and Mount Hood is so beautiful right now because there's still so much snow up there. Sorry, this is called deposition because a deposit happens. You suddenly see a solid and it came from nowhere, and that's because we can't see the gas in the air. So that's called deposition. Another thing about this chart, to go from a solid to a liquid to a gas, you have to add jiggles. So they're jiggling more and more, so you're adding heat. So does anybody remember what the term is when you add heat into something? So it's going into. Starts with an endo. Remember endothermic, positive delta H, and the other direction was exiting, so exothermic. So condensation is an exothermic reaction because you're losing heat as you go that way. All right, what I wanted to talk about is the question underneath says, why is dihydrogen monoxide so special? And so that, of course, is water. And I want to go through it with these states of matter. And the reason this is why water is special, and I'm going to start with the liquid, is water makes that beautiful bend, so the 104.5 degrees. And because of that bend, it does something really special in the liquid state. So what makes a liquid special is it flows. There is definitely movement, but you have high IMFs. So liquids and solids have IMFs. This is true for anything that's liquid or solid, and gases are weak IMFs. And that is because they have jiggles. They have high kinetic energy, high jiggles and giggles, and so they disperse. They're not attracted to each other, or even if they are, because right, they should hydrogen bond, they're all over the place. So it kind of looks like a cat. All right, you can make your water molecules look like whatever you want. I can hear my cat wants me to feed him, so. So that's a big thing that's different, but any gas is going to disperse, and it turns out they actually follow mathematical formulas, and so that's what we'll get to do next week. And I actually moved gas laws to next week because usually we start getting really tired in the 5th and 6th week. I don't even know what week it is. And gas laws are really simple. It's really simple math. We'll do some that are a little bit more complicated, but they're actually, a lot of chemistry books actually start with them. And so as opposed to the math for the solids, the geometry, which is a little bit more esoteric and stuff, the thing that makes a solid special, so a liquid flows, a gas disperses, what makes a solid special is the regular pattern. And that's the lab, well, the homework that you guys had to do, that walked you through it. And then the lab is just you walking through, and you get these regular patterns. And this is why water is really special, is because of this, the strong H bonds, so that's one thing, really strong H bonds, it forms these hexagon shapes as a solid. And this pattern means that the liquid, so H2O as a liquid is the highest density. I don't think there is any other natural substance on this planet that can say that. I know there are some man-made substances, especially some of the plastics, because they don't behave like regular solids and liquids. They're amorphous, they don't have the regular pattern, but I'm pretty sure there's no natural substance in which the liquid is actually denser, and it has to do again with that shape. That shape allows them to stack up like that, and so when you walk through water, you really can feel the water around you when you're swimming. It's actually this wonderful, luxurious thing, and this is why ice floats on water. And so if you made an ice cube, if you had any other liquid in your house, so alcohol, you had to go to a pretty high concentration alcohol, so like a vodka or something like that, and you make an ice cube with that, and then you drop it into the liquid vodka, it will sink. I've done these like at school where we have like all the chemicals and stuff there, but you can make an ice cube out of anything, a solid cube of anything. When you put it back in the liquid, it will always sink because the solid will pack together. And water is really special because it doesn't pack together. The least dense is, of course, this is not shown to proportion. The gas particles are poor little kitty is going to be like really dispersed apart. So this is very low density. Usually the density of gases is like grams per liter. It's 1,000 times, more than 1,000 times, so very low density. And that's true for all gases, that their density is really low. But we can actually measure it and do math with it, which we will do next week. All right. So again, special things about water, its shape allows it to pack. The H bonds, which are really significant, gives it a high boiling point. It's one of the only substances, it's the only one that I know of that you can actually have the solid, liquid, and gas all present here in this room, right? So if you make coffee, you have all three of them present at fairly normal temperature and pressure. And everything else, you have to change the pressure or temperature. And we've all seen solid, liquid, and gas H2O. And it's also so special because it's 71% of you and me and about the same amount on this planet. Yeah. Hydrophobia, we've talked about a lot, and we're going to come back to that. So things that are polar are going to be, the H bond is going to be attracted. So water, because it has this negative area where the oxygen would be and this positive, it's going to have attraction to anything that has a negative and positive area. Hydrophobia would be something that's non-polar. So something that doesn't have this difference in the charge and the pooling is not going to like water. And so they're not going to mix. And so we come back and we're going to look at solubility, and you're probably going to do a little bit of solubility in your kitchen. Back to the question like you asked, Janae, I realize some of the problem is you guys don't have test tubes at home. And so having a test tube rack would make a lot of these things much more doable, but you hopefully have little cups or something like that. All right, the last thing I want to do is these diagrams at the bottom of the page. And some of you have your notes, but the one all the way, oh, my squid hat again. I had no idea it would do this so nicely. All right, it is, the one on the left is for H2O. And this part of the curve, sorry, is we have a liquid on this side and the gas on this side. So this is just like the curve we did earlier. This is vapor, or this is pressure is what they call it over here, and this is temperature. But they add another line, and that is, so you have a solid. So the one we saw earlier, the vapor pressure curve, when we talked about vapor pressure and boiling point, that was just looking at liquids and gases. There's no solids in there. This part of the curve between the liquid and the gas is a curve. Between the solid and liquid, it is a straight line. And there's like math you can do with the slope. What makes water special, because of the density of the liquid, this has a negative slope. It has that downhill. The picture next to it is most things, and you'll see this in the homework, most things you'll have an uphill slope like this. And this means that the solid is denser. So the liquid is denser. So you can think of it, the denser one kind of pushes that down. So here the solid is denser, and pretty much every other liquid looks more like this, the solid, the liquid, the gas. And you'll see questions. There's one or two of these in your homework, and you just answer the questions looking at the graph. This point here is special because that is the point where all three states exist, and it's called the triple point. And again, water is really special. The numbers are given on the graph. It's just barely above 0 degrees Celsius. And so it's a point where it's actually not that hard to reach. And the pressure is pretty low, but most things, the triple points are crazy. Like if you look at the graph next to it for CO2, you have to be at a pressure of 5 ATMs, which is 5 times the pressure that we're all at right now. So you'd have to be like at the bottom of the ocean, and at the same time at negative 56 degrees to have a point where you have the solid, liquid, and gas all existing at the same time. I'm pretty sure in the book that I put on the MyMHCC for you guys, I'm pretty sure they have a picture embedded in there where they show a glass of water with the solid and the bubbles at the same time. Yeah. And then of course you can do all of these. So going from the solid to liquid, remelting. So down here is where the solid is changing to the gas. So that's where sublimation is happening. Or going in the other direction, that's when snow happens. So when we get a cold enough temperature and a low enough pressure, you will get snow because you'll be down in this area. most of the time we're up here, and so we get wet snow, which is sleet and ice and stuff. So questions that you guys have? All right. Well, my suggestion is the practice quiz you guys leave to try on your own and see how you do with it. Well, I guess it's not called a practice quiz because we're not doing any quizzes. But I can either, I probably just post the answer key with notes on it for you to look at. But I think if you try it on your own, I just realized I should make a different one than that, but that's okay. Because it will give you practice. But it's kind of up to you guys. If you want to, we can try it. It's a lot of the same questions we just did. So I think it'd be good to like sleep on this and then try the practice quiz in 2 days and see where your questions are, and then you can ask me. Does that make sense? All right, I'm gonna, unless somebody has a question, I'm gonna stop the recording and I can kick you out. And